Hello, everyone. I am the survey TA Chris, who you know if you take the Monday evening or Wednesday evening labs. But I am here to hopefully add a little something to your studying for this third exam. I thought it might be interesting for some of you if you listen to me go through one of these practice tests and just me going mentally stream of consciousness about how I answer these. Unfortunately, a lot of the organic questions involve some memorization, but just the repetition about how I approach them may be useful. I'm going to be filling out exam 3B that you can find on Blackboard as one of the example tests. The one that you actually take on Monday will be very similar, but will have different questions and likely in a different order. I will encourage you to look through it yourself before you watch this, just to see what your level of knowledge is. But hopefully this will be of use for some people and get a sense for processing all of these. And we will go ahead starting now. Always got to put my name on things. And we'll have to keep folding the test because my camera angle is zoomed in enough that it's more legible. But we'll start off with question number 1. We have the following reaction. Cr2O3 plus 2 aluminum yields aluminum O3 and Cr solid. So, as the substance that serves as the reducing agent. So you're already getting thrown a curveball. We're not asking what is being reduced. We're asking what is the reducing agent. So we probably just want to back up a second and think about what's being reduced and what's being oxidized. Uh, Classically, oxidation was called oxidation because something was having oxygen react with it. So just as a first approximation, I would expect that aluminum is the thing being oxidized. But that's not a great explanation. So we need to remember that oxidation means a loss of electrons. And some people use the mnemonic device LEO, loss of electrons is oxidation. So that's one way to think about it. So we just need to look at the oxidation states of each of these. And I'm going to use some of the explanation space. So we started with aluminum as a solid. So it has an oxidation state of 0. And it led to aluminum 2O3. Now, oxygen is almost always, unless it's in its diatomic form, going to have an oxidation state of -2. So -2 times 3 means the oxygen over here is contributing a -6 overall. And so each of the two aluminum would need to contribute a +6. So the aluminum on this side has an oxidation state of +3. So the oxidation state increased. So yes, aluminum is being oxidized. So if aluminum is being oxidized, that means it's the reducing agent, because everything that is being reduced is an oxidizing agent, and everything that is being oxidized is a reducing agent. So that would be that would explain my reasoning. Aluminum loses electrons, so is being oxidized. Which makes it the reducing agent. And then I'll remember to put up here, the reducing agent was aluminum. So you just always got to remember there's that give and tug, that I'm being oxidized because I was causing reduction to someone else, and vice versa. So then we have our next question here. What is the oxidation state of carbon in the following molecules and ions? And so the trick here is going to be carbon's oxidation state's going to change constantly, but everything else in these molecules is going to have a knowable oxidation state, so we can figure out the answer. So the first one is methane, CH4. And you'll know this because this is organic chemistry. Meth tells you that there's just one carbon, because the standard system of methane, ethane, propane, butane, pentane, hexane, and and methane means there's nothing else special about it, so you just have four hydrogens to fill it in. Hydrogen, pretty much always, unless it's just H2, will have a oxidation state of +1. And so there's four of hydrogen, so the total contribution for hydrogen is +4. That means for methane, to balance it out, the oxidation state of carbon is -4. And now here we have another one, carbon dioxide. We add our little oxygens. Adding the bonds was just a bit of a flare. Honestly, it's actually easier if I just go CO2. Oxygen, unless it's in its diatom or other real specialized, is always going to have an oxidation state of -2. So -2 times 2 means the oxygen is contributing -4. And to balance it out, the carbon would therefore need to be +4. And then we take a look at the carbonate ion. Again, that's CO3. Now we got to remember it's an ion, so there's actually a -2 charge on the whole thing. So once again, I'm going to rewrite it here without the charge for a second. The oxygen has a -2 charge, so -2 and 3 means -6. 3 times 2 is 6. Now we don't actually want a neutral atom, though. We want an atom that has a total charge of -2. So once again, it'll have a +4 charge, because +4 -6 leaves you with that -2 that you expect on the carbonate ion. And we go to the next page. And now we have, CH4 is something in the following reaction. CH4 plus 2O2 yields CO2 plus H2O. Again, as my first gut reaction would be, and sort of a way to double check myself, if something is gaining the oxygen, that probably means it's being oxidized. But we're just going to make sure that we do it again, just playing with oxidation states. CH4, if you remember from 4 seconds ago, means that the carbon has an oxidation state of -4. And then if we look over here, CO2 has the other one, where now carbon has an oxidation state of +4. So the carbon went from -4 to +4. It lost 8 electrons effectively, if you think about it in terms of the oxidation states. So if you remember, LEO is the idea that a loss of electrons equals oxidation. Or the other way to think about it is that the higher the plus number, the higher the oxidation state is. So it increased its oxidation state, meaning it was oxidized. And so I guess we just write A here, because this is A oxidized, B reduced. And we explain our reasoning here is that carbon's oxidation state went from -4 to +4. And a loss of electrons indicates oxidation. Okay, then we have question number 4. You can remove the tarnish, and the tarnish is silver sulfide, from silver spoons by using aluminum metal foil in electrolytic solution of sodium bicarbonate. And we've got the overall reaction here. 3Ag aqueous plus solid aluminum leads to 3 solid aluminum plus aluminum aqueous. And then we just sort of split this reaction in two, and we just keep track of the electrons. So it's extremely straightforward. You just see what the change in the oxidation state is, and you add enough electrons so that the charge on both sides of each half reaction add up. So this was already filled in, 3 silver, which is exactly the same thing as on the top. So we just look to the right-hand side, and we see, oh, that's already filled into 3 Ag. So we just need to look at the different oxidation states. So over here we have 3 silver plus, so that's a plus 3. And over on this side we have 3 silver solids, so that's a 0. So we, just like if we were mixing a molecule together, we have plus 3 and we need to get to 0, so we have 3 electrons, which represents minus 3, and that's balancing out. And then the same thing on this one. Aluminum is a solid, so it's got an oxidation state of 0. And then it leads to, this is not filled out, so we got to look up here. Aluminum 3 plus. So this is plus 3, and so we'll need 3 electrons to cancel that out. Simple as that. We just see we lost 3 electrons here, so we're including them as part of the reaction to keep track of them that way. Now, what do we have next? Draw the reaction of the conversion of propene to propane. Draw all the reactants and all the products. So we get to dive head first into our organic chemistry section now. So first we need to try to shift this over just a little bit because I think I've been leaning in too much, possibly having these dropped off a bit. So first we just look at that prop. So if we remember our system, methane, ethane, propane, butane. So we have 3. So propene means we have 3 carbons in a straight chain. And the E in E means that there's got to be a double bond somewhere. Now, it could be in either spot and they'd be equivalent. So I'll just put the double bond on the far left. So we've answered the prop, we've answered the ene. We've addressed the structure that the name tells us, and everything else is just hydrogens. So this first carbon has 2 bonds, so it just needs 2 hydrogens to get its 4. This one has 3. And the last one, 1, 2, 3, 4. Okay. We could also, this question doesn't actually ask us for the Lewis structure, but it's handy for us to do it this way so that we know exactly what we're looking at. So we could also just say 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So we could just call this C3H6. And we'll do both of them this way. So then we look at the next one. We got, again, prop, so 3 carbons. But now it's just propane. So there's no double bonds, no triple bonds, nothing special, and everything is filled in with hydrogens. Okay, and again, we can just say 1, 2, 3, 4, 5, 6, 7, 8. C3, H8. So we've got one reactant and one product, but we need to draw all the reactants, meaning what's actually happening here. If you just look at the numbers, we're gaining 2 hydrogens. So that should be an arrow plus H2. So there we go. That's the full reaction. C3H6 plus H2 gives you C3H8. And then it says, oh, well, what type of reaction is the conversion of an alkene to an alkane, which is what we just did. And similar to how an oxidation started off as a definition for when oxygen was being added to things, we've added hydrogen to this, so it's a hydrogenation. And we're just adding hydrogen in, so hydrogenation is the term for this kind of reaction. Then we get into even deeper stuff, drawing the Lewis structures of all sorts of organic compounds. The very first one, of course, is one that you can't puzzle apart using the standard naming nomenclature. Benzene, you just are going to have to memorize, but it's a very striking molecule because you've got a resonance structure, which you're not going to have to draw here, but benzene is 6 carbons forming into a hexagonal ring that always looks taller than it actually is when I draw it. And there's alternating double bonds. So you draw a double bond, you skip one, draw another double bond, skip one, draw a third double bond. And then, as always, so that's the basic structure for benzene. And then, as always, then you finish by filling in the hydrogens. And if you look, so this carbon has 3 bonds, so it needs 1 hydrogen. This one has 3, needs 1 hydrogen, 1 hydrogen. So every single carbon on the benzene ring will have 1 hydrogen. And you're not going to lose points if you're a little short on room and you're not getting perfect straightness on these. So there's your benzene, and you will have to draw the whole structure like this. That is the Lewis structure. So if you just draw the skeletal form, then you're not going to get full credit for that. So then we go to the next one, 1-pentene. This one's a lot more straightforward. We can just read it like the little Lego bits of an organic molecule. So first we read pent. So if we remember, methane, ethane, propane, butane, pentane. So that means 5 carbons in our main chain. 1, 2, 3, 4, 5. And then it's not a pentane, so something's going on. We see ENE, pentene, which means there's a double bond. And we got the 1 number, so the double bond happens at the first carbon. And now that we've addressed everything in the name, we fill in the rest with hydrogens. Do, 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 do. And then we go to the next one, trichloromethane. So again, we start off with the base methane. Meth is the first term, so we just have 1 carbon. Methane means there's nothing special like an OH group or something like that attached onto it. So we've addressed the methane part. Then we have to address the first part, trichloro, which just like, tricycle, triangle means 3. So there's 3 chlorines attached to this. And so we just draw 3 bonds with chlorine on them. And so we've addressed everything in the name, and we fill in the rest with hydrogen. Carbon needs 4 bonds. It only has 3 from the 3 chlorine, so we just add an H to it. So there's trichloromethane. Then we go to 2-butanone. So first, again, but. We know that's 4, methane, ethane, propane, butane. And so then we see it's anone. So that's a special name for a ketone. So ketone, it'll be anone as the name ending for it. And we have a number here, which tells us which carbon that the ketone piece is attached to. A ketone, of course, something you'll just have to memorize more or less, or find some way to remember. A ketone is a double bonded oxygen attached to one of the carbons. And so it says 2-butanone. And so I could start from the right or the left, but we'll go ahead and start at the left. So we'll declare this the second carbon and draw that double bonded oxygen. So we've addressed all the parts of the name, and everything else is filled with hydrogen. So 1, 2, 3. This one already has 4 bonds because of that oxygen, so there's no hydrogen on that one. This one just needs the 2, and then 3 on the end, and that's our 2-butanone. Then we have propanal, and Dr. Tease has written, read this one carefully, so we better give it a quick double look. So it's, propanal, and I can see the reason for this. You might, if you were in a hurry, misread it as propanol, which would have indicated an alcohol, but it says propanal, which is an aldehyde. And an aldehyde is a special kind of ketone, I guess would be one way to think about it. An aldehyde is when that double bond with an oxygen is on the edge of one of the compounds. But we're jumping a little bit ahead in that regard. We just need to go with our system. Prop. So we know the system, meth, prop, so there's three of them. Prop means three carbons, and propanal means that it is an aldehyde, which tells us that there is a double bonded oxygen on the edge. So it would not be connected to the center one. And again, I can pick the left or the right carbon to put this on, because if I mirror image this, those are functionally equivalent. But so we've addressed the names: prop for the three carbons and the anal for the double bond. And like before, everything else is just filled in with hydrogen so that carbon has its connections. So this has three, so it only needs one. This has two. And the last one here has three. And we have another wonderful Lewis structure. Next, draw the Lewis structure of a polychlorinated biphenyl. This is probably one that you're just going to need to memorize. That's going to be the easiest method for most people. But for anyone interested, the naming system on here talks about a whole class of compounds. Now, if I'll just do the skeletal model to demonstrate, but if I have a benzene ring and then it is attached to some other molecule, in this case we just write R to mean there's some other big organic structure here, this is referred to as a phenyl group. So if we have a biphenyl, and we got to draw the Lewis structure for this. So I'm going to tilt my drawing this way. So I've got to draw a phenyl group, which is a benzene ring, with some bond to something else, and that bond is to another structure. So there is a biphenyl, but it's a polychlorinated. Now, poly just means it has more than one chlorine on it. Oh, I'm sorry, I almost forgot. This, again, like I said, these are benzene rings, so they have double bonds. So I will just, and these, again, will resonate. So you can just pick any bond to start with. So I'll say this one, and I draw a double bond, skip, draw a double bond, skip, draw a double bond. And then I got to do the same thing over here. Double bond, skip, double bond, skip. Oh. There you go. So, yeah. If you make your meaning clear, you will get the points. Just destroy the mistake. Okay. So there you go. The alternating. And then now you've got your biphenyl, and you need chlorines somewhere. You need at least two of them. So polychlorinated biphenyls are a whole class of compounds. So you can put those chlorines anywhere on here that's valid. So let me just pick a carbon at random. This one has three, so we had one chlorine there. We'll pick another one, chlorine there. Let's do two more. A chlorine here and a chlorine here. So that's great. We've got our polychlorine. So we've addressed everything in the name. So the last thing we do is we fill in hydrogens. This one, because of the chlorine, has four, so it's happy. This one only has three, so hydrogen here. This carbon already has four. This carbon has three. This carbon has three. This has four from the chlorine, and we do the same thing over here. 1, 2, 3, 4. That's happy. 1, 2, 3, 4. 1, 2, 3. So that needs a hydrogen. 1, 2, 3. That needs a hydrogen. The chlorine is good. 1, 2, 3, 4. 1, 2, 3, and that needs a hydrogen. So there's our chlorinated biphenyl. You may decide that you just want to memorize a specific product, or put it together the way I did, where I made all the carbons together, then just added some random chlorines and filled it in. whatever feels like the best method for you to do. Similarly, I will just mention it that the other very large structure that you may be asked about is the polyaromatic hydrocarbon, the PAH. It looks similar, and I'm just going to draw the skeletal structure for the sake of it this time, but it will be bonded in this method here. And you'll have these aromatic rings, and you'll have to make sure that you're alternating the bonds like this, and then this bond is a double bond for both of them. So start there, alternate, alternate. So, but you'll have to draw this Lewis structure if you're asked about the PAH, of course. So just you need to. I recommend just have one basic structure of a PCB and a PAH that you remember, and so when you're asked this question, you're like, okay, this is the structure in my mind that I can put down on the paper. But the next question is for the structure of a chlorofluorocarbon. So the only important thing you need to remember about the chlorofluorocarbons is the vast majority of them are just a single carbon. There may be versions of CFCs that have that, but the most classic structures are just a single carbon. And just they say chlorofluoro. It's an entire class, so it's not specifying exact numbers. So we can just put any of set we want, as long as we have at least one of them. So I'm just going to put 2 fluorines and 1 chlorine on there. And so I've got my fluoro, I got my chloro, and there's a hydrogen left over. So there's a valid CFC. Then I need to write the name of that CFC, but we just look at the name. So it's just a single carbon, so it's meth. There's no double bonds, obviously, because it's just one carbon. There's no double bonded oxygen. There's no alcohol, so it's just methane. And then we just count the things that are added to it. And in alphabetical order, so we start with chlorine, so it's chloro, difluoro, because there's 2 fluorines, chloro-difluoromethane. And you can just think of whatever structure you want as long as it follows those similar rules. Then we go to the reverse now, where we need to name compounds based on their structures. And we got different versions of them here. So our first one doesn't show us the bonds. So we just need to, there's 2 ways we could go about this. One way would be to write the Lewis structure out based on what you see. So this first one says CH3. So C, and recognize that the H3 here is actually structurally bonded to the outside of that carbon. Then we have 1, 2, 3, 4, 5 more of these. CH2, check. CH2, 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 CH3. So this is a long-winded way of just confirming that there's nothing special. There's nothing here except single bonds, carbon, and hydrogen. And so then we count our carbons. 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. So 6 tells us hex. And then there's nothing special. It's a straight alkane, so it's hexane. And so that name then tells us everything we need to know about that chemical. Then we look at the next one. So first thing we do, count out our carbons in the long chain. 1, 2, 3, 4, 5. So 5 carbons means it's something with pent. So then we just run through. There are no double or triple bonds, so it can't be pentene or pentyne. There is no double bonded oxygen, so it can't be an aldehyde, it can't be a ketone. There's no double bonded oxygen with alcohol, so it's not a carboxylic acid. There's nothing else special about that, so it's pentane. But we're not done, because we need to look and see that instead of all hydrogens, there are some fluorine atoms that have been thrown in here. And so I'm going to count these carbons: 1, 2, 3, 4, 5. And then let me see where these fluorines are. There's one here attached to carbon number 2. There's one here attached to carbon number 3. And there's one here attached to carbon number 4. So luckily, this is, I could count the carbons the other way, and then these would be functionally the same. We would still have ended up counting them on a 2, a 3, and a 4. And so we need to let someone know, based on the name, where every single one of these fluorines is located. So we would just name them up: 2, 3, 4, tri, because there's 3 of them, fluoropentane. And I will put big circle around that. So based on that, then someone else would be able to draw that structure out without any problems. Then we come to the skeletal structure, which you got to be just a little bit careful on, because now we have the simplification that anything that's not explicitly called out on the structure is a carbon, and we just assume that there are enough hydrogens to fill things in. So on this little circle here represents a carbon, and we just assume there's 3 hydrogens to fill it in. But so then we count, and it's not the stick portions, it's like the ends of it. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. It's a mistake that even I'll make, where I'll be reading the lines instead, and I'll go, oh, 7 carbons, but this next one's an oxygen. So no, 1, 2, 3, 4, 5, only 6 carbons. 6 tells us hex. 6 carbons, and there's no double bonds or anything like that, but now we've got this special structure: the double O and the OH on the edge. That is a carboxylic acid. And in this case, the end name for that is an anoic acid. So it's hex anoic acid. And therefore, someone could read that name and draw that structure out just as simply. And now we come to these 2 molecules. I will consider them for a moment. And now it wants me to name them. So we will read through the carbons first. Carbon 1, carbon 2, carbon 3. So there's 3 carbons. And remember, meth, eth, prop. So it is prop. And now we've got a double bond in here, so it's not a straight alkane. We got that extra naming, so it is propene for the double bond. I'm going to call it 1-propene because it's there on the first bond. And then over here, we have another, so there's, yeah, and everything else was just hydrogen on this, so that's all there was to say about it. Then we look over here, we count the carbons: 1, 2, 3, 4. So 4 we know means bute. And we look, no double bonds, no triple bonds, no double bonded oxygens, but there is the OH. And we remember that's an alcohol, so it's butanol. And that's all we really need to say to it. We call it 1-butanol because the OH could be in other places. But generally, if you just say butanol, that is indicating the version where it's on the end. So we have successfully named both molecules. And then it says, at room temperature, one of these is a gas and one is a liquid. Which of the 2 molecules is a liquid at room temperature, and explain my reasons? That sounds a lot like intermolecular forces. And dagnabbit, we're expecting you to remember some things that were on the previous test, but it's pretty simple if you remember your intermolecular forces. We can go back here and say, well, what do we have? So we look at this one here on the left. Carbon and carbon bonds are nonpolar. Carbon-hydrogen bonds are nonpolar. So There are no polar bonds anywhere in here. So all you have on this left one is London dispersion forces. Then we look here on the right. We've got carbon hydrogen bonds, but over here we've got carbon oxygen. So we've got a polar bond here, but then we've also got an oxygen to hydrogen bond. That's one of those special ones. So we have hydrogen bonding over here. So the big reason why one of these would be at room temperature is because of the different IMFs. And we can see hydrogen bonding is the strongest. And so we'll say, which of them is a liquid at room temperature? That's the specific question. We'll say 1-butanol, because it has hydrogen bonding, which is the strongest intermolecular force for covalent bonding. And so we have knocked that one out. And we are getting into the home stretch here. We got to draw some more Lewis structures. So again, 2-butanol. So but tells you 4, methane, ethane, propane, butane. So we got 4 carbons. And it's anol, so that tells us it's an alcohol, the OL. And the 2 tells us that on the second carbon. So we've answered everything, and then on the name, and so we fill in all the remaining bonds with hydrogens. This has 3, so it only needs 1 more hydrogen. The next one, ethanoic acid. So eth tells us just 2 carbons, methane, ethane. And then it's an anoic acid. Remember that? The carboxylic acids are the anoic acids. Just a page or 2 ago, we had to draw one of those out. So again, it's a double bonded oxygen, and then an OH attached onto the end one. And so we've answered the whole name, and everything else is hydrogens. This carbon already has 4 bonds, so it's great. This one only has 1, so it's got to get 3. And that one's complete. Now we're getting a little bit more tricky. So just again, pent, the last portion. So pent tells us that there are 5 carbons on our main chain. 4, 5. And pentane, so there's no alcohol, there's no aldehyde, no ketone, no double or triple bonds. So all we're left with then is the 2-methyl. So just like if you had a single carbon all on its own, you would call that methane. But if you have a single carbon that is attached onto a longer chain, then you get the YL, methyl. And we see it's number 2. So we count to the second carbon, and we just add another carbon. As simple as that. And so we've answered 2-methyl, pentane, and then we just fill in the hydrogens. This carbon also needs hydrogens now. 1, 2, 3. This carbon only needs 1. And now we have propyne. So again, prop tells us we got 3 carbons, methane, ethane, propane. And the YNE, propyne, tells us that we have a triple bond. We didn't get a number for it, and that's because there's only 2 locations that a triple bond could be at, and no matter which one I put it on, I could flip the molecule around and it would be functionally the same. So it's my choice as I'm drawing the Lewis structure. I usually prefer to put things on the left-hand side, so I'm just going to draw the triple bond here on the left. So I've got the prop, I've got the yne, and I just fill in the rest with hydrogens. This has 3 bonds, so it only needs 1 hydrogen. The middle one has 4 bonds already, so it's happy. And the last one just needs the 3. And then Dr. Teese is apparently trying to weed out anyone whose brain has been completely fried by just giving you methane, but it's the exact same process. So meth tells you one carbon, and it's a methane, so nothing special. No special groupings or anything like that. So there we go. We're done with the name, and we fill in the rest with hydrogen. And now we have the last page with the special bit, which will definitely be on your version of the test too. I can just about guarantee it. Not the exact same molecules, but the same general process here. We've got to draw the Lewis structures of propanoic acid and methanol. So let's start with the hard one first. Just prop tells us 3. So we have 3 carbons. And it's anoic acid, so it's a carboxylic acid. So that means we add the oxygen here and an OH here. So we've addressed the name, and we fill in the rest with hydrogen. Make sure every carbon's got its 4 bonds. They all need 4 bonds. There we go. And then methanol. So meth tells you there's 1 carbon, and then it's anol, so it's an alcohol. Methan. Then yeah, the OL is really what you're looking for the alcohol. So I have to add an OH group on to the carbon. So we've addressed the name, and the carbon still needs 3 more bonds, which you just fill in with hydrogen. And then draw the Lewis structures of the 2 products that form when propanoic acid reacts completely with methanol. So this is a special reaction that you got to remember, where what's going to happen is the OH on this molecule and the OH on this molecule are going to link together and create an oxygen inside the middle of a carbon chain. And so over here, I'm going to start by drawing the propanoic acid version. So carbon, carbon, carbon. The double bonded oxygen still here. And then we have 1 oxygen in the middle. And then the next portion comes in. So we just have 1 carbon from this. And what we took out was 1 hydrogen from here and an OH from here. So the other product is just H2O, or if we draw the Lewis structure of water. But again, so going back to here, I've addressed just all the main chain pieces. I got to fill in the hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. So, and then we've got to name the 2 products. So this product we have here is referred to as an ester. You may remember that name from the biodiesel lab that you did this week, where you took 1 ester that was, it was 3 esters all linked together, and then you switched them into 3 separate ones, the trans-esterification. The ester has to do with this carboxylic structure, but then something else attached onto the end of it. And so there's a special naming process that you need to remember for this. And I don't know, again, don't know a perfect mnemonic system for it, but I specifically drew it this way with the carboxylic acid on the left because the part that has the double oxygen bond onto it is sort of considered the main part of it. So this piece, so this part here on the left is the main structure of our name. So 1, 2, 3. 3 carbons is our main structure to start off. So that's prop. And again, it's a propane, because there's something else in here. It could be, propanol, etc., etc. Then we address this part, that it's an ester. So The special name for these esters is an anoate, so it's propanoate. And I'm leaning down. So this is the main structure, the propanoate. But remember we added methanol onto it. I'm going to flip back real quick. So we have to address this part too. Just like before, now this is a meth that is now a piece of a larger structure, just like we had a 2-methylpentane earlier in this test. So this is a methyl propanoate. And that is just the name that you have for it. Just you're gonna have to just remember the O8 one as another one of those special organics, but you'll only have one question structured like this. And that is the end of this particular test. And hopefully just me continuously counting the number of carbons over and over will give you a just sense of the process for most of these. Not exactly Khan Academy, but I will hope that this is somewhat beneficial to a few of you if you stay to watch it. And I guess as a reward, someone was joking about a face reveal, so I will flip that up. And hope that you guys will have a good test on Monday.